Good morning. It is Saturday the 31st of October and it is time for our live tutorial. This is Physics with Keith from under the stairs somewhere in Essex. It's good to see we've already got a couple of people dropping messages off. I can see that's Lex there, Freya and Wombat.com, and you can see that I've got the chat thing working now. Last week we had some problems with that, which rather affected interactivity, but this week I've got it working again. I won't bore you with the details, but it looks like Chrome updated things in a way that didn't actually help. Anyway, I fixed that now. So we've got my new microphone, so hopefully the sound is coming through okay, but do drop me a message if there are any sound issues that come up, if you can't hear anything. I was asked last week to look at magnets. I believe that was to A-level, sort of A-level difficulty magnetism, from somebody, I can't remember who it was, someone who hadn't tuned in before, so certainly not a regular that I recognise the name of. I asked for a little bit more guidance, magnets being a vast topic, and there was none, so I don't know exactly what bit of magnets you want me to look at. So what I thought I would do is to start with some of the things that cause students some problems, and we'll take it from there with a few questions as we go along. Now, I'm going to start at GCSE level, and then we'll move on to some of the early A-level stuff. What I've discovered in teaching for more than a decade is that there really isn't that much difference between the GCSE and the A-level stuff when it comes to magnets. When it gets to electromagnetism, that's when A-level really takes off and gets a lot more complicated. But the magnetism side of things isn't that much, isn't very different between GCSE and A-level. So when I do start talking about A-level stuff that is exclusively A-level, if I get onto that today, then I'll make that clear, and I'll ask first, and if no one wants me to go into it, then I won't. There's no point me doing things that people don't want. So, without any further ado, let us begin our tutorial about magnets. Now, first of all, let's ask you all the question, what about magnets do you already know? Wombat.com is taking A-level physics. That's super, so you're probably going to benefit from going into the stuff that goes a bit further. Have you already studied magnets? Let's ask that as a question. Not for a while, not at A-level, just GCSE. Yeah, okay, so we're basically starting from the beginning here then. So I've got some slides that I produced for my GCSE students. Don't get too hung up on the fact at the top it says AQA GCSE 9 to 1. This is for all of the different GCSEs. It's just that happens to be what we teach within my school. So you can see here the most fundamental idea that students find challenging, which is Fleming's left-hand rule. And before we get into what these different fingers mean, we need to dig into what this B part means in particular, some of the real basics of magnets. And then, so we're going to rewind a bit, then we're going to fast forward to here. And when we look at this topic, I'm going to ask you lots and lots of questions, and you're going to feel a bit weird, but I'm going to want you to use your hands during the session. This is my left hand, by the way. I don't know whether it's being reflected so that you can tell it's my left hand, or I have to get my head around this now. When I look at this, it looks like my left hand. Yes. It hasn't reflected my face in the little webcam. So you're going to be using your left hand here. So you're going to feel a bit awkward sitting at the computer messing around with your hands, but it's going to help me understand or find out whether you understand what's going on. So let's rewind a few pages, right back to the absolute beginning, and let's rattle through some of this stuff. Whoops, that's too far. Let's rattle through, and I've gone and opened something by accident. Brilliant. Let's rattle through this nice and quickly. So hopefully that's all still visible there. Yep, good. Right. So first things first, magnets. North Pole and South Pole. The reason why there's a North Pole and a South Pole, the reason why you can't have a single North Pole or a single South Pole is rooted in what magnetic fields really are, which is a consequence of special relativity, which we will not be going through this morning, but if you're interested, I can always put that in a later tutorial. Some wonderful videos out there already from Minute Physics about what magnetic fields really are, if you're interested. But the basics of magnets is there's a North Pole and there's a South Pole, and the magnetic force that's produced from the magnetic field is strongest near or greatest force near the poles and weakest away from the poles. So that's the first bit. That's a basic. Let's move on to this bit here. Again, doesn't get much more basic than this. Unlike poles attract, South Pole attracts a North Pole. North Pole attracts a South Pole. Like poles repel, so North Poles repel each other, South Poles repel each other. So far, this is, I think, Key Stage 2 level. You first meet magnets in primary school and you play with them and you put them together and you get repulsion, you get attraction. It's all very exciting when you first meet magnets because they are exciting. We're not going to waste time looking at this. Let's move on to this part here, which is what happens when you put a simple iron bar into a magnetic field. So around this magnet on the left, which has got a North Pole and a South Pole, which I've coloured here for your convenience. Around a magnet, there is a magnetic field. A field is just a region in space where a force is produced. So a gravitational field is a region in space around a mass, which produces a force on other masses. And an electric field is a region in space around a charge, which produces a force on other charges. And so a magnetic field is just a region in space around a magnet that produces a force on other magnets. So that's what a field is. So how does a magnet attract iron, steel, cobalt and nickel as well? How does a magnet attract them? Well, it attracts them by turning that iron bar into a little magnet. It's called magnetizing. It magnetizes this iron bar. And the reason why that works is because iron, through reasons that I won't even go to with my A-level students, there are many factors that affect how substances interact with magnetic fields. But for some reason, iron, when you put it into a magnetic field, gets magnetized to support that magnetic field. It tries to make the field stronger by becoming a little magnet itself. If I were to put copper in this magnetic field, it would actually do the opposite. Very, very tiny bit. You'd barely notice it, but it actually does the opposite. And carbon does the opposite, and almost everything else does the opposite, apart from iron, cobalt, nickel, and there's one other, but I can't remember it. But it has a small effect like this, where it reinforces the magnetic field. Iron, cobalt, and nickel are the three that you learn about at GCSE and A-level. So there's videos you can find on YouTube where strong magnetic fields can be used to make frogs levitate and things like that. And that's because frogs, mostly made out of water mostly made out of oxygen and a bit of hydrogen thrown in there, and iron, nickel. Yeah, no, Wombat.com, the steel contains iron. That's why that's included in that list. It might be, I don't want to say because I might get it wrong, but I think it might be platinum has a very, very, very small ferromagnetic effect, but I'm not sure enough to commit to it. And that's why it's not included in the big three of iron, cobalt, and nickel. As I say, the only reason steel's included in that list is because it's an alloy that contains iron. And not all steel does. Not all steel is ferromagnetic, incidentally. Anyway, so iron bar becomes a magnet, and it becomes a magnet to reinforce that magnetic field so that it has a south pole attracting the north pole here, and that's why an iron bar will be attracted. And if I were to place an iron bar next to a magnet orientated the other way, it would be magnetized the other way. So far, so good. We know about some of the basics of iron, of magnetization and fields. Now, hands up who's seen a picture like this before. There must be something else then, Wombat.com, I'm thinking of. I'll have to have a really good think about this. So, Wombat.com's seen this before. Lex has seen this before. Not sure if Freya's seen this before. Freya's never seen this before. Okay, well, let me tell you what this is. This is a bar magnet. Just like we saw before, bar magnet. And you place a piece of paper on top of the bar magnet and you sprinkle some iron filings onto that paper. And the iron filings all line up in these lines, allowing you to visualize the field. And remember what a field is. A field is just a region in space where a force is produced. So if I switch across now to some fields that you probably are a bit more familiar with, if this is the Earth, there's the Earth. We might draw a gravitational field as being a bunch of arrows pointing towards the Earth, like this. And we could say that if there is any mass placed in this field, it feels a force in the direction of that field. So, oops, that was slightly wonky, but okay, that'll do for now. Here's my gravitational field. There's the Earth. And so if I draw, oh, I don't know, some sort of asteroid here, and I just let go of this asteroid at this point here, a force is produced on that asteroid in the direction of the gravitational field. But if I were to put the asteroid here, the force would be produced in this direction here. So that's what gravitational field does. We can switch out the mass in the middle, which at the moment is the Earth, and we can switch that out and we can say that that's a charge. So let's get rid of all these lines. And let's do exactly the same thing with charges. So if I have a positive charge, think fast, name a positively charged particle. If I have a positively charged particle here, around it is a field. Now the field is in this case in the opposite direction. It's going away from a positive towards a negative. But that's an electric field. Proton, proton, good, good. All three. We've got a full house of protons. So here's my field lines going on. This is electric field. So a completely different field altogether. It doesn't interact with mass. Only interacts with charge. So if I place a positive charge particle here, it feels a force in the direction of that field line. And that's why positive charges repel each other. Newton's third law tells us that if this force is produced on this charge because of the interaction, then an equal magnitude opposite direction force is produced on the other charge because of the interaction with the first one. So Newton's third law tells us why there are two forces. But it's this one here we're interested in. The positive charge feels a force in the direction of the field lines. And there's some rules about field lines for charges. But mass doesn't interact with this field, in the same way as charge doesn't interact with the gravitational field. Now for magnets, it's a little bit more complicated. So if I take a magnet and I drop it down, oops, that's not a bar, let's do this. If I drop a magnet down here like this, and I label one side my North Pole and one side my South Pole, the field lines now do not start at one point and go off to infinity, like they did for gravitational fields, like they did for electric fields around a point charge. Here, the field lines behave very, very differently. They're a very different field. So the field lines come out of the North Pole of a magnet, go around, then go back into the South Pole of a magnet, and they connect. Well, that was terribly drawn. They come out of the North Pole, go around, go back into the South Pole of the magnet, and connect. And you would see there would be fields coming around, going in, and now I've got to try and draw these without them crossing. Oh, great success. Like that. So we've got our fields doing this. Out of the North Pole, there'll be another field here going like this, and I'm not drawing all of them. Coming out of the North Pole, the fields go into the South Pole. But the rules are the same. So a gravitational field produces a gravitational force on mass. An electric field produces an electric force on charges. A magnetic field, which is what I've just drawn, produces a magnetic force on magnetic poles. So Wombat.com says, is there a reason why it is north to south rather than south to north? Is it due to Earth's gravitational field? Sort of. It's by convention. When magnets were first discovered, we believe that was in ancient China, lodestone, which was dug out of the ground, and an ore of iron, which is magnetic, and you suspend it from a piece of string, and the lodestone will rotate. And one side would face roughly face the geographic north. So that was called the north-seeking pole. We could just as easily have decided to label everything back to front. It wouldn't have mattered. Same way, Wombat.com, if I decided to have the field lines going from South Pole to North Pole and everybody on Earth decided to agree and have that as our convention, all of our physics would still work exactly the same way. But by convention, we've labelled North Pole, South Pole. We labelled North Pole, South Pole based on which way a lodestone rotated in ancient China. And then we decided, well, let's draw the field lines going out of the north and into the south. And that's all we've got to it. So if I place a magnet into this field, something happens. Now, this is where it gets a bit weird, because I can't just place a North Pole here and it feel a force in this direction here. I can't do that because I can't get a North Pole by itself. I can only get a North Pole connected to a South Pole. So if I get a piece of iron like this, which has got a North Pole and a South Pole, so it's already magnetized, North Pole, South Pole, then the North Pole, which I've drawn on the top here, is going to feel a force in the direction of the field lines. The South Pole feels a force in the opposite direction to the field lines. And so what's going to happen to that little magnet? What's going to happen to that little magnet? I mean, it might do eventually, but what's the first thing that's going to happen to this magnet? Let's imagine I put the magnet, okay, right in the middle here, North Pole, South Pole, so it's right in the middle. I've got a force in that direction, a force in that direction, and it's equidistant from the two poles. So we've got... Oh no, you're very welcome, Finley, and I'm glad to hear that you managed to get an A star. That's really good to hear. Well done to you. So Lex says rotates to align with the field. Yes, it will rotate to align with the field to reinforce that field. Well, lovely message from Finley. That's really made my day. That. So let's delete this one. Let's leave this one here. So this whole magnet's going to rotate. Isn't that awesome? An A star. Doesn't get any better than that. Now, the magnet itself, this little magnet, will have its own magnetic field. So if there's another magnet nearby, it's going to line up as well. And another magnet nearby is all going to line up to reinforce that magnetic field. So you end up with all these little magnets twisting around to line up to form a straight line. Well, to form a line along the field line anyway. If we just drop iron filings, that's if you file a piece of iron, you get these little flecks of iron off called iron filings. If we drop some iron filings on here, the iron filings become little magnets because they become magnetized, and then they rotate and they align each other. They align along those field lines for the same reason. And it produces images like this, where you've got these beautiful field lines. Okay, so let's move on then. We've got some what happens when you put field lines like this: North Pole, North Pole, North Pole, South Pole, and so on. We're going to move on from that. You're all far too kind. Far, far, far too kind. I'll be screenshotting this and showing my boss and saying I want a pay rise. No, I won't really. I wouldn't give me one anyway. So the picture we've got here, we've got a bar magnet, we've got little plotting compasses all the way around it. Those little plotting compasses show the direction of the field. If I just zoom in, or as I like to say in my lessons, I will bigger it. That's fine. Where's my zoom button gone? It's probably in here. Zoom. No, that's zoom out. Let's zoom in. Control and plus, apparently. Bang, bang, bang. There we are. Now you can see it a bit more clearly. We've got the North Pole here, and you can see that these little plotting compasses are pointing away from the North Pole. And if I scroll across, you can see the plotting compasses are all sort of pointing towards the South Pole. So you can use these plotting compasses to sketch out the shape of the magnetic field around a zoom out, control minus, to plot the shape of the magnetic field around a magnet. And when you do that, you get the shape that you saw with the iron filings as well. So there's two different techniques for determining the shape of the magnetic field around a magnet. We're going to skip these bits for a moment because we've done the basics of magnets. So let's move to this finger here then. What's this all about? Well, it turns out magnets and iron filings aren't the most exciting thing that you can do with magnets. Because they're not the only thing, iron filings, iron isn't the only thing that interacts with a magnetic field. It turns out that current does too. Now, this was a massive mystery when it was first discovered. A huge mystery of why it is that current will also feel a force in a magnetic field. So these fingers, B, we've now talked about. B is the direction of the magnetic field. Out of a North Pole into a South Pole. That's what B is. So if I've got current flowing in a direction perpendicular to our magnetic field, what we call the direction of the magnetic field, B, at A level you'd call that the flux density, but we can just say it's the direction of the magnetic field, then there's going to be a force produced on that current carrying wire. Now, you want to know why that is? I can scroll backwards and I can show you how around every current there's a magnetic field, and it's the interaction of those two magnetic fields, but you really don't need to know that. You need to know what B is, magnetic field from North Pole to South Pole. And you need to know that if I place a current carrying wire into that magnetic field so that the current is perpendicular to the direction of the field line, and it has to be perpendicular, then a force is produced on that wire. And the weird fact is that the force is perpendicular to the current and perpendicular to the magnetic field. So what I want you all to do, everyone who's at home watching, is to get your left hand. You see there's 4 of you out there at the moment on the internet, 4 of you watching this. Get your left hand and play along with this. You'll thank me one day, maybe. Well, you might do, Finley did. Take your left hand, and what I want you to do is to do this. So it looks like you're pointing at someone, like you're pretending you're a, I don't know, cowboys or something. Pew, pew. Okay, so you've got your fingers like this. And then extend, rather impolitely, your middle finger so that it is 90 degrees to your index finger. So what you've now got is your thumb 90 degrees to your index finger in that direction, and your middle finger 90 degrees to your index finger in that direction. And of course, they're all 90 degrees to each other. Let me full screen my face so you can really see what I'm doing. Okay? 90 degrees. 90 degrees. So there we go, there's the other one, 90 degrees. So you've got your 3 fingers I can't really extend this thumb out any further to make it 90 degrees, but that should be 90 degrees, like that. Now, this is called Fleming's left-hand rule. And in GCSE questions and in A-level questions, if you are asked why a force is produced on a current-carrying wire in a certain direction, you can answer by saying, because of Fleming's left-hand rule. I can come to that in a little bit, Wombatcom. I will do. I will come to that in a little bit. So, by the way, it's not the fields that feel the force. It's whatever's producing the fields that feels the force. But we'll come to that. So we've got our three fingers like this, and there's different ways of remembering it. The little mnemonic that's here is FBI, which I suppose would help Americans more than it helps us. I'm not a fan of the FBI one. I was taught first finger, which is this one here, the index finger. First finger, field. Then second finger, this one here, current. And then thumb for the force. But I don't know if that's going to be any help to you at all. So if we have a magnetic field pointing in a certain direction and we have a current carrying wire, we can now determine the direction of the force on that current carrying wire. That's what we're going to do. So let's start with some notation. We're working in 3 dimensions, so this is going to be difficult to draw. So to make it easier, we draw pictures in 2 dimensions, and if something is going into the screen or into the page, so that this direction as you're looking at it, into the screen, then we use the notation of an X. X means into the screen. If something is coming out of the screen towards you, then we use a dot. And the way to remember this is the back end of an arrow, the flight of an arrow, looks like a bit like an X. And the front end of an arrow, there, I don't know if that's a very good arrow. I'm not an archer, so I'm not very good at drawing arrows. If I looked at the arrow from this side, that's an eyeball, I would see a dot. If I looked at the arrow from this side, I would see a cross. And so a cross means going away from us, and a dot means coming towards us. So towards you is a dot, away from you is a cross. So what we're going to do is we're going to start with a region of magnetic field, which I'm going to draw with an X like this, which is going into the board. Okay, it's going into the board. And I want you to imagine that I've got a current carrying wire going through this region and carrying a current in this direction here. So I'll use I to indicate the direction of the current, and I will use B to indicate the direction of the magnetic field. What I want you all to do is to type an answer, but don't press enter yet. Ah, you've ruined it. Okay. Next time, type the answer, but don't press enter. Then I want everyone to enter at the same time. It doesn't matter. It's okay. It's okay. I want everyone to press enter at the same time so that I know that everyone's having a go at it. It's all good. So first finger field into the screen, into the board. Second finger current, which is to the right. So into the thing to the right, and then the force, yeah, you're right, the force on this particular wire would be produced upwards. This wire would feel a force upwards. So let's try that again, and this time I'm going to switch some things around, and I don't want you to give the answer straight away. I want you to type the answer, but don't press enter, and then press enter when I say go. Oops, that's supposed to be an arrow. So we've got a region of magnetic field like this. And I've got a current carrying wire carrying a current at 90 degrees to it in this direction here. So work out what the direction of the force is on that wire. Type your answer, but don't press enter. I'll give you 10 seconds. 9, 8, 7, 2, 1. Press enter. Yep, towards you. Perfect. Towards you. You wouldn't say up or anything like that because that could be confused with that direction up. So you'd say this way's towards you, isn't it? Again, it's the camera having to invert things longitudinally is really difficult to do. So towards you is correct. So let's try another one. Let's have our magnetic field pointing downwards. Oops, that's not quite downwards. Oops, that's not quite downwards. So we've got our magnetic field pointing downwards. Let me just twist this around a bit. Oh, come on. Stand by. Downwards. Okay, now I've got my current carrying wire carrying a current into the page, into the board, into the screen. So type your answer, but don't press enter. What's the direction of the force on that wire? You really have to contort your arm to be able to get the answer to this one. Okay, got 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. Press enter. To the left. Beautiful. To the left. Perfect. Freya's not dropped an answer off there yet, or at least the answer hasn't come through yet. Left. That hurts your hand. Yes, it does. Yes, it does. Yeah, left is... it's an awkward one to contort yourself, but I think that's the hardest orientation to get your hand around. I have to put my elbow right up. If you're in an exam, you're allowed to do that, but try not to make it clear what you're doing, because otherwise you might be accused of cheating. But you're allowed to use your hands. It's the only way to do this, really. Right, let's do another example. So this time I'm going to have my magnetic field going, let's do it like this, going into my page. It's a little bit less painful for us. And this time I'm going to have a beam of electrons. And my beam of electrons is going to be moving into the magnetic field in this direction. So there's my beam of electrons. And I'd like to know what the direction is of the force on that beam of electrons. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Press enter. Interesting. So, unanimously incorrect. And let me explain to you why. These have negative charge. Therefore, the current is actually in this direction here. Yeah, current is the opposite direction to the flow of electrons. So first finger field into the screen. Second finger is our current, which is that direction. So the force is down. Sneaky, yes, but it's a sort of horrible sneaky trick examiners play. So electrons travel the opposite direction to the current. Current is the rate of flow of positive charge. Okay, let's do another one. So let's have our magnetic field going into the page because that's slightly less painful than anything else. Let's have a string of alpha particles travelling in this direction. So it's a beam of alpha particles travelling in that direction. You've got 10 seconds to decide the direction of the force on those alpha particles. And if you're thinking, what's an alpha particle? Guess! I will tell you, but you're going to have to guess for now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, go. Okay, perfect. Did any of you guess? Or did you know? You knew. Okay, good. So, yeah, helium nuclei is what an alpha particle is. Particle physics, my favourite topic. Helium nucleus is going to enter our magnetic field, travelling from left to right, because they have positive charge. In fact, it's 2 plus. Because they've got positive charge, they are going to feel the force upwards because they're the same direction as the current. Right, last one. Last one. So we're going to have our magnetic field going down. I want to do some maths in a second with you. So we've got our magnetic field going down. Oh, I've done it again. Like this. Let's just move this arrow across to the left a little bit. There we go. So uniform magnetic field. It's a brilliant topic. I could talk. I recorded a 2-hour long... it was an hour and a half, I think it was. Let's call it a documentary, all about particle physics and the standard model for my kids in my school. I told them to watch it. And I think about 4 of them did, because I did drone on for a bit. You know how I like to drone on. Okay, so here's our picture. I'd like to know the direction of the magnetic force on this wire. A wire carrying a current downwards. The magnetic field is downwards. You've got 10 seconds to decide. 10. Type your answer but don't press enter. 9, 8, 7, 6, 5, 4, 3, 2, 1. Go. Wombatcom has got it correct. Lex doesn't know. That's because there is no force. There is no force. Freya's not sure. There is no magnetic force on this wire because your fingers have to be perpendicular and they're not. So the amount of force can be determined using this equation. F equals, and I'll write it in the form that it appears on GCSE syllabuses, BIL. F equals BIL, where B is the flux density. Remember, that's just a way of quantifying how strong the magnetic field is. But we can now give it its correct name. Flux density. Complicated. Oh, wow. How have I written the word density there? Complicated sounding name, but for us, it's just a way of quantifying how strong the magnetic field is. That's going to be in units called Tesla. I is our current. We've already discussed current. We know what current is, measured in amperes or amps. L is the length of wire that's in the magnetic field. And we can measure that in meters. And when we use flux density in Tesla, we use current in amperes or amps, and we use length in meters, it gives us a force in newtons. And this will give you the magnitude of the force. It will not tell you the direction of the force. You've got to use your left hand for that. Okay, so for A-level students, there's one extra little thing we can add to this, which is that at A-level, you might have pictures where the current is at some sort of angle. Okay, there we go. The current is at some sort of angle to the magnetic field. Why can't I just drag that? Come on, you can do it. I'm not going to give up. I'm going to succeed. There we go. So Absolutely. That's right, Wombatcom. Absolutely. So what we need is the component of current, whatever that means, because current is a scalar, but now's not the time for us to fuss about that. The component that is in that direction. So if we know, depending on which angle we're given, if we're given this angle, the angle that the current makes to the perpendicular, then this here is just going to be I multiplied by cosine of that angle. But if we were given this angle instead, then this part here is going to be I sine of the angle. So it does depend on how that angle is given to you. Whether it's given to you the way it is in the blue one here, that might be getting a little bit small for you there. Let's bigger it, zoom in. There we go. Or the way that it's drawn with this red angle. So you'll have to either use sine or cosine depending on how that angle is given to you. Very often it'll be given in the blue way there, so your equation would become BIL sine theta. But don't rely on that. So will the non-perpendicular current directions subtract from the force though? No, they have no effect. There's no effect from them at all. So the only component of the current that affects the magnetic force is the perpendicular component. So we have to add a term on to resolve your vector to find the perpendicular component. That's all we're doing there. If you want it a little bit more formally, because I can't help myself, this is the sort of thing I like to do, a little bit more formally, I would prefer to say F equals I and then L cross B, where that's the cross product of L and B. I is a scalar, L is the displacement of the positive charge that's flowing, and B is the magnetic flux density, and F is now a force vector. So I would prefer to say it like this, but we don't use that in A-level because in A-level physics we can't assume you understand what vector products are, cross products. That's A-level mathematics. I think it might be A-level further mathematics. I'm not a maths teacher, so I'm not sure. But it's certainly not on A-level physics, which is a real shame because I think it should be. Okay, so there's a little bit of mathematics for you. The next part here is just some questions. So what I'm going to do is I will leave these on the screen for a second. If you want to, you can work through those questions. It's some basic rearranging equations sorts of questions. You're given 3 of the terms and you need to calculate the 4th. You can type your answers if you want to. You don't have to. The next slide I'll show has the answers. So I'll see if you've got any questions at this stage. If there are no questions, then I will switch it to the answers slide, but you can always pause it before you get there if you want. Next week, it would be good if we could move on to electromagnetism, because magnetism and electromagnetism, I think they should go quite closely together. And we'll again start with GCSE electromagnetism, but then I will put a bit of A-level in. It will get complicated with the A-level. So I'll do the GCSE stuff first. So Freya says no questions. Any questions from anyone else? It doesn't have to be about this, of course. It could be about any other part of the physics. Just mute my microphone whilst I pour myself a drink. No questions? Brilliant. And it's no problem, Wombat.com. The A-level, really, what's quite nice about physics is that in primary school you learn a little bit of physics. You don't do a very good job of it because you haven't got the mathematical competency to be able to access the physics at the level that you need. And then Key Stage 3, you do the same physics, but you start introducing some basic mathematics and you try and get the concepts right, Newton's laws, that sort of thing. Then GCSE level, the level of mathematical competency grows, and the demand on your ability to construct answers that are carefully written so the physics is correct, that demand increases. And so it's just a spiral. Then we go around again for A level, and the mathematical complexity grows again. Still just linear algebra. There's still nothing too complicated about it. No calculus or anything. But you sort of, in a way, you add another dimension to the problems, and your answers have to be that little bit more correct. And then when you get to degree, you just loop around again. You do the same topics, but you just keep adding complexity. Key Stage 3, you do motion in a straight line. In Key Stage 4, you start looking at motion where vectors are important, two-dimensional motion. In A level, well, you can see that the mathematics starts going into 3 dimensions. When you do your degree, you start looking at 4 vectors in general relativity. So each stage, the mathematics gets more complicated, and the style of your answers has to be better. You have to be more correct. You can't use woolly language in your answers. But the content is the same, and so when it comes to tutoring physics, I'm quite happy to do GCSE, then loop around and add a bit more onto it for A level. There are a few topics where that's not possible because they don't appear at GCSE level, but magnetism and electromagnetism do, so let's do it properly. Right, okay, I'll show you the answers then. You can always cover your eyes if you don't want to see the answers. And then I will see you next week, 10 o'clock, for electromagnetism or any other questions you want to send through. Please do tell your friends to subscribe to this, to get involved with this, because we had 3 people joining in and a 4th person, Finley, just saying some nice things. Very welcome, but very nice things. The more people we have joining in, the better it will be, and we'll get more questions, and then everyone benefits. So please do promote this. Okay, thank you very much. I'm muting my microphone. I'll show the answers, then I will just stop the video feed. Have a good week. Stay safe. Probably point out that significant figures aren't necessarily correct on this. Apologies.